sixth week where we're gonna begin our journey with petsc. So what is petsc? So petsc is a collection of library data structures routines for solving large nonlinear algebraic systems, and the whole library is sort of built around the MPI interface, that is the message passing interface, which enables one to run their programs over multiple processors, and we'll see some examples of that. So yeah, I mean, it's being used in a host of different toolkits libraries such as AddFlow, Codaster, CoolFluid, Phoenix, Fluidity, FreeFem, Moose, MoFem, OpenFOAM, and so on. So this particular library offers you a lot of tools with which you can achieve great computational speed, efficient memory usage, all through a very easy interface through the C programming language. So we're working on Windows, but we can use the Windows subsystem for Linux to install Ubuntu as an app. So I have it installed already. So when I launch Ubuntu, I'll be greeted by this. So this is my desktop on work. I mean, this is my Linux sort of virtualization inside Windows. All the Linux commands work quite well. So it's something Linux users don't have to do this. You can directly install petsc. So let me just walk you through on how you would go around installing petsc. So first of all, I'll assume you have GCC installed. So on my PC, I have GCC 7.5.0, and in petsc on this website, you have to go to installation. All right, so how to go about installing this? So first thing, you have to download the thing. So you have to install Git. You have to get the latest release, and once you get the latest release, you have to you have to unzip the thing, okay, because you'll download it as a zip file. Once you unzip it, you can configure it like this. You have to sort of build the set of files that you've downloaded. All right, so the configure statement tells what C compiler it has to use, what C++ compiler it has to use, what Fortran compiler it has to use, whether it has to download MPI, whether it has to download BLAS and LAPACK. So I'd suggest to keep the configure statement as it is shown, so that the MPI that you may already have installed does not conflict with the MPI that you will install through this particular build. Alright, so once you do that, you do a make all check, and then you follow whatever you see on screen. So eventually you will end up with lines such as this. You will do this particular thing. You will configure it with petsc arc and petsc dir, which specifies the petsc directory and the petsc architecture. So once you start installing, you'll actually be prompted to use those. So keep a note of those. The variables that you will be requiring are petsc dir. So for me, it is installed inside this, right? And the other thing will be petsc So it command not found, but this is the thing. So in fact, the working directory for petsc where it is installed, it's petsc dir slash petsc slash bin, and inside this, so if I do this, I will have all the different. So inside this, I will find MPI exec. So I must use this particular version of MPI to run the programs over multiple processors. And in fact, if I don't want to do that, you may not wish to run this over multiple processors, but then what's the use? I mean, the true power of petsc comes in when you're running it on multiple processors. So you must use this particular MPICH, or rather MPIXC. So you must use this particular MPI exec to run your program on how many processors you want. All right. So we'll look into this a bit later. But this petsc dir and petsc they will be prompted to you once you start installing. All right. So you can fetch which MPI version you're using. But yeah, I mean, if you're building it like this, you will have to use this particular MPI. Otherwise, it will not sort of, because it's not the MPI that is already installed, it's not compiled with petsc. Rather, petsc is not compiled with that. It will not run it on multiple processors. Well, this is a very easy workaround. You can go to your bash rc file and you can declare the MPI exec version to be this particular version instead of the default version. But anyway, all those are minor issues, right? So nowadays you have petsc running on iOS or Android, so it's really going scalable. You can use GPUs, NVIDIA AMD GPUs. So they've done a wonderful job of creating a massively scalable library, and it's not a recent library. It's, I think the first release came from the year 1994. So it's something which is quite old, and it has been developed over decades. All right. So yeah, so let me go back to, let me create a new folder in C. So let me go to my, let me make a new directory. All right. So now I've created a new directory, and you can do two things. You can, of course, work within this terminal. If you're comfortable with it, you can use um, any editor. So suppose I want to create a file, let's say lec29.c. So, or let's give it something more descriptive. So the first example that I want to do is finding out the value of an exponential using a series approximation, a Maclaurin series. So what I can do is I can use Emacs, and I can say Taylor, no, not Taylor, exponential approx dot c. So what this does is it will open the editor inside the terminal itself, and if you're comfortable using Emacs, you can do all the programming here itself. But if you're not comfortable doing this, you can go to your Dropbox directory. I mean, see, not everyone may be comfortable doing things in the terminal, but you can go to the Dropbox folder, you can create the file over there, and you can compile it simply on the terminal. So what I mean is, now I can go to the terminal and I can create a new file over here. So I can call it something like this, and I can use any editor that I want. Notepad++ is a very light editor, and I can create the code over here as well. Alright, so if I save this, I should be able to see uh, the file over here as well. Okay, so if I do emacs expo, so I have the hash include stdio.h over here. Alright, the color contrast is a bit off, but that's okay. So let me exit. So I'll do it in over here, no problem, and we'll just use the terminal to compile our things. So let me clear all this. Yeah. So we want to create a file which will help us approximate an exponential. So the Maclaurin series is as follows. So E is summation 1 by n factorial n equal to 0 to infinity. This is the way you have to define it. So let us first create a C program which will help us to do this without using petsc, and then we'll see the petsc version later. So let us include math.h. So int main return 0. So now we need to declare some variables. All right, so int I double e. So let us store the solution inside e, and yeah, let us declare it as 0. Let us initialize it as 0. So let me change the theme. Right, this is a much better contrast. So what we can do is, inside this program we must do a loop over this. So we must declare what n is going to be. So this sum is obviously we cannot do till infinity, so let us do the sum till capital N. All right, so let me declare n as a integer as well. All right, so now we must do for I equal to 0, I less than n, I plus plus. So then we must do e equal to e plus 1.0 divided by, so we must do a factorial of I. Alright, so we must not define what the factorial function will be because we don't have those predefined in C as such. I mean, of course you can use the GNU scientific library. There's something called as the GSL, which also gives you a host of libraries which are useful for computations. But anyway, we don't need to do that. So we need to define what this is, and in the end we have to print. So we'll do printf percentage f slash n, and we have to print e. So far we have not defined what factorial will be. So we must declare long int, and the reason I'm using long int because factorials tend to become really large. After a while, the values of factorials, it becomes really large. So we will declare fact, and it will take as an input integer, let's say a. All right, so it must return something, so return r. So long, okay, so we don't need to do this. So the way to do a factorial is, if a equals 0, right, or a equals 1, then we must return 1. Else we must return a times fact of a minus 1. So this is a recursive way of defining the factorial of a number a. Alright, so this is nothing but recursion, because once a is large, is neither 0 or 1, it will simply, suppose a is 3. What happens? Suppose a is 3. So it will call fact 3. So when we call fact 3, it will check whether 3 is 0 or 1. If it is not, then it will go to this. So it will then return 3 times fact 2. But 3 times fact 2 will involve 3 times 2 times fact 1. So if you unroll the function stack, this is what you will see. And something like this you might have done in your first year programming or even 11th, 12th. But regardless, I'm just showing you how one would go about doing this for those of you who have not done it. But I highly recommend you grab hold of a C programming book to understand what is really going on. So this is the factorial way of writing it, and I'm assuming some working knowledge of C programming in this. This is not really a course where you will learn C programming, right? So yeah, that's pretty much it. Then we will go to our terminal. Let's do GCC. Then let me clear the screen. So GCC expo. Alright, let's simply do this. Let's see if there's some error. There's no error. /a dot out. But I have not defined what n is, so there will be an error. Okay, so I have not defined what n is. So I must define n as a certain number of terms. So let us say 5. Let me save this. So it gives us an approximation of 2.70833. So if I increase this, let's say to 10, let me recompile and let me run the file. We get a much better approximation. In fact, let us increase the number of decimal places that we can print. So let us say 3.15f. So we'll get 15 decimal places. So let me recompile. Alright, so this is what the approximation is. So this is how you can evaluate an exponential using plain C language. So we have not done anything fantastic. In fact, we can use int argc car star argv. So we can pass command line arguments to do certain things. So through this command line argument, we can avoid doing this, and we will simply declare n to be an integer. But what we will do is we will pass how many number of terms we would like. So n would be a to I of argv1. So argv will be storing as strings the things you will pass. So argv0 is always the name of the function. Argv1 is the first argument that you give to the function. So that is why, so everything else will be treated as string. So you have to use a to I, so argument to integer. Alright, so let's compile this and see how we can do this. So let me save this. So let me do GCC. Okay. And well, the reason we have this error is we've not included the standard library. So hash include stdlib.h. Alright. So now we should be fine. Excellent. So now when we do this, we must pass the number of arguments. So I can pass 20 as the argument. So So if I say 2, I get an approximation of 2, because when we have n equal to 2, what we have is e equal to 1 over 0 factorial plus 1 over 1 factorial, which is 1 plus 1 is 2. So as we increase the number of terms, so if I make it 5, we get this. If I make it 20, we get this. If I make it 50, we get this. And yes, this it does converge to the value of the exponential. So suppose now you want to print out all the variables, not the variables, but the intermediate values as well. So let us say you want to print the partial sum, right? So we go over here, so we say printf partial sum equal to percentage 3.15f slash n, and we will pass e, right? So let me recompile. So that's the partial sum. So the partial sum converges quite quickly. So let us also print the iteration number, iter percentage d slash t, and I'll print the iteration number over here. So this will allow us to see how those partial sums are evolving. So let me compile it. Let me take 10 terms. So first term 1, 2, 2.5, 2.6. So very quickly you see you get 10 to the power minus 5 accuracy after just 9 terms, right? So what happens when we don't use long int? I want you to find this out. If I don't use long int, and let me just give you a quick answer to that, but you should ideally go ahead and print them out. So let me just print out percentage ld slash n, and I'll say percentage t slash t. I'll print I, and I'll print fact I. Alright, so let me comment out this line. We don't need the partial sum. I'm just trying to show you how large those integers are. Still, it's not that large, so maybe for 20. Okay, so integers quickly become quite large. And if you do not use a long int, you'll run into floating, or rather um, overflow exceptions, because you're overflowing the range that you can represent using the number of bytes GCC allocates to integers. So that is why you need to use a long int. Great. So one thing which I forgot to show, we can find out the actual error. What we can do is we can write down the exact value as returned by the math library as exponential of 1, and we can print out the error, the absolute error, as percentage e minus exponential of 1. So let us save this. Let me compile. So the error is 10 to the power minus 7. Forgot a backslash n, new line carriage. Let me recompile. So the error is 10 to the power minus 7. So for 10 terms, that is. So let me say 20 terms. 10 to the power minus 16 is machine precision. So this small program helps us get the job done. We have not made use of any multiprocessor things. We have just created a function, and it uses recursion to find out factorials. And we have used a very simple accumulator. So this E is actually an accumulator, because it's accumulating the partial sums. This is finding out the partial sum. This is how we accumulate. So now we will move on to the parallel implementation using petsc. Let's create a new file, and we call it expo petsc.c. So we're gonna use the inbuilt petsc data types and commands to find out the approximation for exponential. So first things first, hash include petsc.h int main and int argc argv. So every sort of petsc code that you write has to eventually finish with return petsc finalize. So this command helps you to gather all the threads. So because you'll be using the MPI either explicitly or implicitly with petsc, you have to do this petsc finalize. If you don't do this, you will get very weird behavior now and then. So don't forget to do this. So it's sort of almost mandatory. So then the next thing we will have will be petsc initialize. Rather, before initializing, let us declare some variables. So the first variable will be the inbuilt data type petsc error code IERR. So the petsc error code is something which is 0 if everything is working properly. If it doesn't work properly, then it will return 1, 2, depending on the error type that you encounter. So it's ordinarily of type int, but there is some additional data structures associated with the data type petsc error code. So this is something which you'll be using as well. Then we need int rank to hold the rank of the processor that we're working with. Additionally, we'll need I for running a loop. So why do we bother with the rank? So suppose you want to find e equal to summation 1 by n factorial for n equal to 0 3. So essentially what we'll have 1 by 0 factorial plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial. So what our strategy will be is to declare 4 processors or 4 processes, and each of these 4 processes will have a certain rank. There will be some process with rank 0, rank 1, rank 2, rank 3, right? So once you do have these ranks, then what will happen? We would like to find the factorial of this rank, or rather 1 by factorial of this rank, 1 by factorial of this rank, 1 by factorial of this rank, and 1 by factorial of this rank. So once we have these 4 factorials, we will then gather all the data that the different processes have. So it will simply sum over all this. So it is essentially it's a reduction operation over going from 4 processes to one process, one central process. Okay, this is what the strategy is. So hence we need to hold the rank of the process inside this. Right. Then what we will do is, okay, we need a double data type for the eapprox and the local factorial. Okay, so you'll see what it means just in a while. Then what we will do is initialize the, so we'll initialize petsc, meaning it will create all the MPI it will run in background all the MPI initialization steps. So petsc initialize, the arguments to initialize will be, and so the address of argc, the address of argv, then the petsc database, in this case it is null, then the help text. Alright, so this is how you would initialize. So most of the initializations will look like this, nothing much will change. Okay, and you can look in the function reference to see exactly what it does. Okay, it initializes the database and MPI, and it has to be the very first line. Takes in inputs as argc, argv, the pointers to them, the address of those, then the database file and the help file. Yep. You can also pass it as null, but so if you type down the executable and write minus help, it will push this string or whatever you've written. And what we do is, so we've initialized this, we've created all the NPI things in the background, so we don't need to bother about all this. So after declaring this, we have to usually check for an error. If there is an error, so the way to do it is chk erq IER. So it checks whether there is some error. Okay. So now what we'll do is we will create the ranks. So we will create the ranks ERR equal to NPI from rank. So it will create the different threads. Okay. And the way to declare this is petsc from world. Then we will pass the address of rank. Then we will, as usual, check for error. So this particular line is important. It will create all the threads that we need depending on how many threads we ask the OS to allocate to this particular program. So it will store all the different ranks of the thread inside the address of rank. So after this point, we will have n number of threads working together. Not together, but in parallel. Okay. Now we will do local fact equal to 1. So for each thread, the factorial has to initialize with 1, or I equal to 2, I less than rank plus 1, I plus plus. Then what we will do is local fact equal to local fact divided by I. Essentially what we are achieving through this. So let us look at it. So suppose rank is 3. Then what is it? So for I equal to 2, so let us see, local fact is 1 initially. So then so it enters the loop with I equal to 1, lf equal to 1, local fact equal to 1. When I equal to 2, it does local fact equal to local fact by I. So local fact is 1, I is 2, so it does this. So the loop will execute from 2 to rank plus 1 minus 1. So I equal to 2, I equal to rank plus 1, I less than 4, I plus plus. So it will execute a loop going from I equal to 2, I equal to 3, that's it. Because the loop will execute till I less than 4, that is till I equal to 3. After this I equal to 3, the local factorial will become lf by I. So lf is already 1 by 2, so 1 by 2 divided by 3, so it is 1 by 3 factorial. So this is how we can achieve a local factorial using simple loop. And this all will execute for all the different parallel threads that you will create. It is not running for a single processor. All this will execute for all the multiple processes that you will create. So we have local fact. And so what we can do now, we can print out what rank of the thread is and what the factorial it has written. Let us do that. So we will use petsc printf petsc self, because for each thread it has to execute. So petsc printf has to execute for each thread, otherwise it will show some behavior which is not controllable. We need to pass this definite. Then as usual, percentage d slash t percentage lf, because we're directly finding out 1 by factorial. Right. So slash n, then we'll say rank and local fact. Yeah, so that's pretty much it. Now before compiling this, we need to create a make file. I've already created a make file. Let me open it with Notepad. The make file contains these lines. It will always contain these lines. It will contain the variables, the rules, and the target will be first to create the object file, and it will link the object file to the executable with the help of this. Then it will make use of the libraries of petsc, and finally it will remove the object file. We don't need the object file. We just care about the exponential, about the executable. Okay. So the way to run this make file is very simple. We have the target name as expo petsc. So we just say make expo petsc. Okay, there is an error. Let's see what the error is. So it is unused, no problem. And there appears to be some error. Ah, we have not called IERR, but okay, this should work. Great. So it's just showing a warning because E approximate we have not yet called, but that's okay. So now what we can do is we can use MPI to launch those many number of threads and find out the factorial for each thread. So the way to do it, I've shown this earlier as well. Let's see there. We have to use the appropriate MPICH, let's see arc, then MPI exec minus n, let's say 4 threads, and the executable is so we have created 4 threads. So 0 thread and 1 thread return 1 obviously, 2 returns half, returns 1 by 6. So everything looks fine. We can create more threads despite my computer being having 4 cores. We can create 8. You can create more than that as well, and you can verify all these are correct. So you will notice that the ranks are not printed in sequence, and that is why. That is because once you call a printer, so all this is, remember, after initializing or declaring the number of threads, all this runs in parallel for all the threads. So whenever a certain thread is able to do this computation first and go to this print, it will execute this print statement. For threads which will take more time, it will appear after one. Okay? There is no synchronization among the threads, and that's something which parallel programming you have to always account for. Okay? There is no synchronization. Once you start doing this kind of things, you will quickly realize you have to do a lot of hard work to synchronize all the things. So you have to do a lot of thinking, pre-planning, and all. But anyway, so for now, we have all the different threads giving us all the different factorials. So now we must accumulate all the different factorials. So the way to do that in parallel environments is to reduce all the threads to a single thread. IRR equal to MPI all reduce. So now to all reduce function, we must pass the local facts, the addresses of all the local facts. So local fact, we must pass the address of the variable where we want to store all the reduction variables. So after reducing all the local factorials, we want only one sum, and that is ER. So we must pass the address of the approximate. Then we must pass how many, what each local fact, how many elements each local factor, that is 1. Then MPI double, that is the data type. This is the data type of finally what kind of reduction we must do. There are various kinds of reduction, there are products, there are sums. We must say that you must sum Finally, we must pass the com world. Alright, once we've done this, we can check for error. Alright, so with the help of this function call, it will take all the local factorials, do a sum, and put it into EAP. Alright, so finally we can simply print EAP. So once we've obtained a single thread, we can simply do printf percentage 3.10f slash n. Let's see. Could we print it again? So okay, so it's outputting the final print statement a bunch of times, so you must do something about it. So what can we do about it? So what has happened is it has executed for all the number of threads that we have. So instead of this, we will use petsc printer, but we will use com world. So com self is using all the different threads. So self implies all the different threads that you have. But we will do this. Let's see printer. Let's see com world. So once we use world, it will use the merge thread to find to only print it once. And using this, we're gonna say e approx is percentage lf slash n, and we're gonna print out here. So petsc printf, by passing com world, we're gonna print out only one, the output from only one thread. Alright, let's see what we can get out of this. So 2.18, let me take more decimals. Okay, let us see what the, let us copy this. E exact. Let us print out what E exact. Right. So if we use more number of threads, obviously the error will reduce. But yeah. So through this small program, I've shown you how to sort of use some simple aspects of MPI. And in case you're not so interested in all this, don't worry, because once we start using petsc, you will quickly see that even running programs using a single thread, they're very fast and very efficient. So in the later lectures, maybe we'll just focus on one thread. But if you are interested in speed, you can always do this MPI exec and allocate a large number of threads. But you know, later on, because you'll be using a bunch of inbuilt solvers, you can pass only one thread, you can get the solution, no problem. In the later programs, we'll not be using this kind of reductions and all this. Typically, we'll avoid doing all these reductions. So whatever MPI business needs to be done will be handled by petsc in an inbuilt fashion. We will not be exposed to all this kind of declarations, then merging and all this. So, but anyway, this lecture, I hope to have shown you how to include petsc. This includes all the libraries inside this header file. I've shown you how to initialize, how to declare error codes, how to print using different threads, how to reduce, and how to make a make file. So make file always will look something like this, and how to execute, how to compile it using a make file, how to execute a file. So it's a very sort of simple lecture. It may be confusing in the beginning, but once you start using it, once you get um, the hang of what MPI is, this particular program will seem very easy. Even if you have not understood all of this completely, in the next class, we'll not be exposing ourselves to all this um, thread splitting, thread merging, and all. Well, but all this will still exist, petsc1 and all, because if you do use MPI, petsc will internally allocate to the solver whatever number of threads it has to be. So with this, I end this particular lecture, and I will see you next time with a new lecture, and we'll actually solve a one-dimensional problem using pets. Bye.